Now children, this part is very important, and the next videos, the topics which will come are very important. Gauss theorem or Gauss law in electrostatics. Now what Gauss law states? Gauss law says the total electric flux coming out of this closed surface, right? Now this is a closed surface. In this the charge enclosed is this Q, right? So total electric flux coming out of this closed surface is equal to the product of charge into 1 upon epsilon naught. Or you can also define it in this way. The surface integral of electrostatic field E produced over any source over any closed surface S. Now this is your surface S, enclosing a volume V in vacuum. That is, you can even learn this definition. The total electric flux phi over the closed surface S in vacuum is 1 upon epsilon naught times the total charge Q contained inside or enclosed inside. Now here we have taken capital Q. So you can write this capital Q. This capital Q may be in the sum of Q1, Q2 number of charges, right? That is distributed here. But the entire charge is concentrated at this point O, and this is a sphere. We are proving Gauss law for spherically surface only. This is proved for spherical surface only. So this is a spherical surface whose radius is R. Out of this S area, we have taken this as a small area which I written here as ds. Now this is the point P where this area is considered. This is the charge Q. From this charge Q we are calculating the electric field intensity at this point P. What is the value of electric field intensity at point P? That is kq upon r square. You know electric field intensity at a point is kq upon r square. Now at this point P, where we have considered small area ds, so radius vector in terms of unit vector is in outward direction. Electric field is always normal to the surface, this we already seen. Unit vector of this area vector, it's in outward direction. So in place of n cap you can also write ds vector. That is also in the outward direction. That is, area vector and electric field both are in the same direction. So we have to find out what is the value of total flux which comes out of this. That will be the product of charge enclosed multiplied by 1 upon epsilon naught. The charge which is outside to the surface will not contribute in the flux. And this surface we call it as Gaussian surface. What do we call this surface? Spherical surface as a Gaussian surface which is of radius r. Now if we use this formula which I written, phi E equals to surface integral E dot ds equals to q upon epsilon naught. Now this is the first definition here. This is the second definition which I said. The total electric flux coming out of a closed surface area is a product of Q into 1 upon epsilon naught. So in flux only that charge will contribute which is enclosed inside the closed surface. The charge which is outside the closed surface will not contribute in the flux. So phi equals to surface integral E dot ds equals to q upon epsilon naught. Now if I take this part, I start from here to prove that this part and this part is equals to this. I will start from here. If I start from here, that is phi E equals to, if I take for this small part and I assume here that E into ds. Now E into ds both are in the same direction, right? So this is the flux which is coming out through this small area. Now if we have to calculate the total electric flux, now you want to write this, you can even write this part in this way. d phi E. small flux coming out of this small area, right? Now when you have to calculate total electric flux coming out of this enclosed spherical surface of radius r, then this equation has to be integrated. When this equation is integrated for total surface, we write it surface integral E dot ds. This will become phi, that is total flux coming out of this entire surface, surface integral E dot ds. Now ds is your area vector. Now simplify it. If you simplify it, phi E equals to surface integral E dot ds. Now in place of E, we can write kq upon r square, or you want one more step to be written, you can write in this way. E ds cos theta, A dot B, AB cos theta. Now what is theta here? Theta here is 0. That is the angle between E and area vector. Both are in the same direction, so theta is 0. So what form this equation will take place? E ds. Now put the value of E here. This is much more easier for you. In place of E, you can write kq upon r square into ds. This kq upon r square could be taken out. Now this you got from this equation. So I'll just add this part. This part from here you got this, here you got this. So E dot ds, you can write one step this way so that it will be in continuation. From this E dot ds, you got this. So phi equals to this, E ds equals to. Now in place of this, you already written kq by r square. So this kq by r square will come out since it's not changing into ds. Now surface integral of this ds, that is, this is small area, and what is the total area of this? That is 4 pi r square of a sphere. So what will we get? Phi E equals to surface integral E dot ds. In place of k, we can write 1 upon 4 pi epsilon naught, where epsilon naught is electrical permittivity of free space. 2 pi r square. In place of this, we can write 4 pi r square. The terms which are cancelled, you can cancel them. So what final relation we got? E dot ds equals to q into 1 upon epsilon naught. This is the proof of Gauss law. Now this charge could be as a sum of multiple charges which are enclosed in this. So again, if you just state the Gauss law, Gauss theorem in electrostatics, what Gauss law says that the total electric flux coming out of a closed surface, again I repeat, the total electric flux coming out of a closed surface is equal to the product of charge enclosed. This is very important part. Charge enclosed into 1 upon epsilon naught, right? And this part of Gauss theorem we have proved only for spherical Gaussian surface. Is it clear? Next video we'll talk about the applications of Gauss law. So this is the proof. Clear?